So in section 3.6, we're going to learn to differentiate the logarithmic function, and we'll also learn something called logarithmic differentiation, which is really cool. It's actually a nice, powerful way to do things. Sometimes you can make things a little bit easier, and we'll compare that with one that we did for Audrey a little bit before class started. Here's some reminders of your basic rules for logarithms: product rule, quotient rule, etc. At this level, we have to distinguish between the product rule for logs and the product rule for derivatives. But your rules for logarithms in terms of differentiation are up here. Now, when we differentiate a log, let's start out with the easiest formula, I suppose. If I was differentiating the natural log, so d by dx of the ln of x, derivative of the natural log is pretty nice. It's just 1 over x. Now that changes a little bit when we start working with logs of a different base. What base is understood to be here with the log, the natural log? E. So if you're dealing with something other than base E, say base B or B is whatever, then not only do you get 1 over x, but then you have to multiply it by the natural log of that base. Now you can see that this one's a little bit more general than this one, because if the base was E, what would happen to the ln of E? ln of E is equal to 1. So this one would default to this one in the case that your base is E. You can extend this and make this a little bit more general. If you've got the log of some function of u, then it's 1 over u times the derivative of u with respect to x. So the derivative of the outside times the derivative of the inside. Or you could write that like this. Derivative of the natural log of g is 1 over g times g prime. So in any case, let's play around with some derivatives here. We'll start out with f of x is 3 times the sine of ln of x. So again, you've got an outside and inside function. You're going to have to use a chain rule on this one. So let's see. Matt, what's our outside function?
Would it be log of a, or?
Actually, you're looking a little too far inside. The outside function would be your sine function, right? Oh, okay. So derivative of the outside is going to be cosine of 3 ln of x times the derivative of the inside. So let me just write that as is. So here's our derivative of the outside times d by dx derivative of the inside, 3 ln of x. Now what happens when we differentiate a constant, or when we have a constant as part of our function? Yeah, derivative of constant is 0. So if you use the product rule, you're really only getting half of it. Basically what we're going to do is we're going to look at 3 times the derivative of the natural log. What's the derivative of the natural log?
1 over x.
1 over x, thank you. So cosine of 3 ln of x times 3 times 1 over x. There's not much you can do to clean this up. Maybe I'll put the 3 and the 1 over x out in front. So 3 over x times cosine of 3 ln of x. But that's it. It just doesn't really clean up in any real nice friendly way. Let's try the next one. Derivative of log base 10 of x to the 4th plus 1. So let me find a little real estate right up here. F prime of x is going to be 1 over this function, x to the 4th plus 1. But we're stuck with that different base there. It's not log base e, it's log base 10. So then we have to multiply this by the ln of 10, which is annoying, times something else. What's that something else?
Derivative of the inside.
Derivative of the inside. So we got the derivative of the outside times the derivative of the inside. Ethan, why don't you finish it up for us? What's the derivative of the inside?
4x to the third.
4x to the third. So 4x to the third over x to the fourth plus 1 times the ln of 10. And again, no real dramatic simplification on this one, so we'll just leave it here. Nice. All right. I want to hint at some things to come here in terms of example C. So we're going to do this a couple different ways. First of all, we're just going to tackle it head on. Before I get going on this, no matter what I do, I'm going to rewrite the cube root of x. How do you think I could rewrite the cube root of x? X to the 1/3. Okay. So, yeah, let's see. I'm going to do that over here in a new sheet. So, example C. F of x is ln of x to the 1/3. F prime of x, that's going to be 1 over x to the 1/3 times the derivative of x to the 1/3. And this thing is out of ink. Let's try this one. D by dx of x to the 1/3. So what's the derivative of x to the 1/3?
Third x to the negative 2/3.
Yeah, well done. So 1 over x to the 1/3 times 1/3 x to the negative 2/3. Okay, so this becomes a little chore of some algebra here. Let's see what we can do. Personally, I guess I would get rid of the negative exponent. I'm going to write that 1/3 all the way out in front. 1 over x to the 1/3. What do you have to do to get rid of the negative exponent? Yep, put it in the denominator. So 1 over x to the 2/3. Is there anything else I can do? What happens when you multiply things with the same base? What do you do with their exponents? Add them. So 1/3 plus 2/3 gives me x to the first power, or basically 1 over 3x. So that's one way to do this. But the reason I wanted to do it this way first is to try and emphasize that it's a real good idea to use your properties of logs. That's why I gave you this sheet that reminded you of all your properties of logs, in particular these, that if you use them, they can help you out. So let's see if we can't redo this one, trying to use our properties of logs. Let's see. So we'll revisit this. F of x is the ln of x to the 1/3. Is there a property of logs I can use here? What can I do here? Lillian, any thoughts? Any properties of logs that can help us out?
I'm not sure.
Yeah, how about the power rule? Let's bring that exponent out in front. So that's going to be 1/3 ln of x. And now let's look at f prime of x. Well, we're going to look past the constant. It's going to be the constant times the derivative of this function. Julia, what's the derivative of this function? What's the derivative of ln of x? You can look at your sheet if you need to. I know this is brand new.
1 over x?
Yeah, 1 over x. So I get 1/3 times 1 over x, or 1 over 3x again. Wow. Wait a minute.
That was easy.
Yes, absolutely. All right. So the moral of the story is you definitely want to try and use your properties of logs when you can. it's gonna help. It's gonna make your life easier in terms of calculating the derivatives. All right, let's keep going. Let's flip it over to the other side. So example D here. So let's take a look at example D. This time I've got the ln of x times e to the negative 2x. And let's see what we can do with that. Any suggestions to get started? What would you suggest I get started with? Lath?
Can you separate natural log of x and natural log of e?
Sure. Let's use the product rule to get started, right? I mean, why not? It's better to use the product rule here than it is to do it with derivatives. So it's going to be ln of x plus ln of e to the negative 2x. Now, a lot of times for my algebra students, I'll write this not with ln of x, but I'll write it a little bit differently. I'll write it as log base e of e to the negative 2x, just because this is a little less abstract than this is. There's some nice simplification with this second term. What is it? How's that going to simplify?
You can simplify the natural log in e because it's to the base of e.
Right. So really what we're doing here is we're using our inverse properties. If you have the log of something to power and these bases match, that is the base of the log and the base of the exponential function, if they match, then these are inverse functions. They cancel each other out. You just get the exponent. So what's the exponent for us in this case? Negative 2x. So it's ln of x minus 2x. And differentiating this is going to be a lot easier than what we would have had to have gone through to start with. So let's go back over here. Y equals the ln of x minus 2x. What's the derivative going to be?
1 over x minus 2.
Yeah, 1 over x minus 2. Wow, that wasn't bad at all. I can't overemphasize for you enough that it's helpful to use the properties of logs. If you didn't, then when you differentiated this, you'd have to do 1 over x times e to the negative 2x times derivative of this, which would require not only the product rule, but the chain rule. So it'd be a lot of work there. This is a lot nicer. Now, this is going to kind of hint at our next little trick, which is called logarithmic differentiation. Let's talk about that for a second. So, logarithmic differentiation. Now, you don't necessarily have to copy this down. What I'm going to try and give you is the gist of things. Suppose you have y equals some function of x. Okay, not so bad. You want to find its derivative. But f of x is some kind of messy function for which, if we had some logarithms involved, the properties of logarithms could help us out. So what we'll do is we're going to take the log, natural log, on both sides. So we'll do ln on both sides. And then I'm going to apply my derivative. I'm going to take the derivative of both sides. So d by dx says I'm going to take the derivative of both of these. We're fresh off our work in section 3.5 where we're working with implicit differentiation. So who wants to take a shot at the derivative of the natural log of y here? What's going to happen?
1 over y times y over dx.
1 over y, that's derivative of the outside, times derivative of the inside, which is your dy by dx. Thank you, Sailor. Over here, I'm going to get 1 over f of x times the derivative of f of x. 1 over y dy by dx equals f prime of x over f prime, or over f of x, etc. Now I'm pretty close to what I wanted. I wanted to get dy by dx. So what I'll do is I'll multiply both sides by the reciprocal of this. In other words, I'll multiply both sides by y. dy by dx equals f prime of x over f of x times y. And you know what y is because you started out with y. And yes, in this formulation, it looks like you're going to get some cancellation. That's fine, you do. But what we'll do when we're doing these problems in practice is we're going to replace y by whatever function we started out with. And then we'll have our derivative. We'll have dy by dx, that's f of x times f of x, or divided by f of x, that'll cancel, will equal f prime of x. So it's a sneaky way to get the derivative, but the nice thing is that by using the product rule and the quotient rule for logs, a lot of times you can get some simplification that makes this calculation a lot easier. A lot easier than it would be without it. So we'll start with example E. So example E, we've got y equals the square root of x minus 2 over x to the, is that 6th? X to the 6 plus 1. Personally, I would start out by writing this as x minus 2 over x to the 6 plus 1, all raised to the 1/2. And because you've got an exponent and a quotient, those things are kind of amenable to the rules for logarithms. So I'm going to take the natural log on both sides. ln of x minus 2 over x to the 6 plus 1 raised to the 1/2 power. Okay. Let me star this. And just put a little reminder here. It's at this point you want to use your properties of logs as much as possible. Use properties of logs, logarithms, as much as possible. Okay. Well, what properties of logs can I use here?
Quotient rule.
We can use a quotient rule, but before we use a quotient rule, we got to do something with the 1/2. Yeah, so we'll use the power rule first. So the power rule is going to take that 1/2 out in front. So it's going to be 1/2 the ln of x over 2 x to the 6 plus 1, like that. Now I can use the quotient rule. So, okay. And let's see if you guys can catch my mistake. 1/2 ln, so it's going to be log of the numerator minus log of the denominator. So just the quotient rule there.
You go 1/2 just 1.
Oh, yeah, there you go. So that 1/2 multiplies this logarithm. So So either you need parentheses or you need to distribute that 1/2 to both of those terms. Initially, I didn't have that 1/2 distributed to both terms. So it's just something to be a little bit careful about. A lot of times people have done so much work that they think, hey, we're done. But we haven't done any work with differentiation at all yet. None. So now it's time to work with the derivative. Let's remind ourselves here that we're going to be differentiating with respect to x. Even though I've got a y here, I do have to take care with differentiating the y. So let's apply the derivative to both sides. That is, take d by dx on both sides. Sasha, maybe you can help me out. What am I going to get when I differentiate ln of y with respect to x? So it's going to be derivative of this function, so 1 over y, that's the derivative of the outside, times, I'm sorry, I didn't hear that last part. Derivative of the inside is going to be your dy by dx term. So derivative of the outside times derivative of the inside equals 1/2. I'm a Balaji. How about the next one? What's that one going to be when I differentiate this? 1 over x minus 2 times what? Well, in this case, you're going to take the reciprocal of this, so it's 1 over this times the derivative of this. What's the derivative of x?
1 over, it's gonna be 1
Deriv-
minus 1.
Derivative of x minus 2.
1.
1, yeah. Oh, 1, thank you. And then likewise over here, 1 over x, or excuse me, 1/2 times derivative of the log function. Try and write that down before I write it up here. Give yourself a chance to calculate that one.
You maintain the 1/2 on the outside.
You could, sure. You could keep it factor. Nothing wrong with that. So, Max, what's the derivative of this one going to be?
1 over x to the 6 plus 1 times 6x to the 5th.
Good. 1 over x to the 6 plus 1 times 6x to the 5th. Let's see. Let's clean this up just a little bit. You could factor out the 1/2. I'm kind of torn. Factoring out the 1/2 is fine. Also, it's all right if I cancel that 2 into this. But let's factor out the 1/2. Let's go with Saylor's suggestion. 1/2 times 1 over x minus 2 minus 6x to the 5th over x to the 6 plus 1. And that's going to equal 1 over y dy by dx. I remember being kind of amazed when I first saw this. I'm like, wow, it just works out, and it will. Our original goal is to calculate dy by dx. We don't have dy by dx by itself yet. What do I got to do to get dy by dx by itself? Multiply by y. So if I multiply both sides by y and 1 over y cancel, it gives me dy by dx equals 1/2 times 1 over x minus 2 minus 6x to the 5th over x to the 6 plus 1 times y. but we prefer to have things in just terms of x. So the last step I can do is to replace y. What should I replace y with? Yeah, all the way here back at the beginning. Square root of x minus 2 over x to the 6 plus 1. Square root of x minus 2 over x to the 6 plus 1. And that's it. All done with that one. Don't forget this last step, please, to replace y by our original function of x. But there you go. Now, I have no idea how tough it would be to do this without implicit logarithmic differentiation, I should say. But it probably wouldn't be a lot of fun. We had to do a little bit of work up front to rearrange this with our properties of logarithms. But once we did that, differentiating this was pretty easy. And then we had to do a little bit of house cleaning, that is to multiply both sides by y and replace y. But overall, it's not too bad compared to what it could have been. But we're going to take advantage of a problem that Audrey asked earlier, and just see for sake of comparison how hard it would have been with logarithmic differentiation versus without logarithmic differentiation. Before I get there, are you okay with example E here? Okay. So here was Audrey's problem. It was, and we'll do this in place of example F, so we'll call this example F. We'll call it F prime, right? It's not quite example F. H of x is 2x minus 3 to the 4th times x squared plus x plus 1 to the 3rd. And we want to differentiate this using logarithmic differentiation as opposed to just the product rule and the quotient, or product rule and the chain rule. So I'll have to take the natural log on both sides. We'll call this y. ln of y is going to be equal to ln of 2x minus 3 to the 4th times x squared plus x plus 1 to the 3rd. Can I kind of fast forward a little bit on the simplification of the logarithmic term here? Is that okay? What two things do you see you're going to have to use in working with the natural log on the right-hand side? Product rule followed by the power rule. Absolutely. So the product rule followed by the power rule. So the product rule is going to be the log of this plus the log of this, and then the exponents come out as well. So fast forwarding a little bit, it's going to be the ln of 2x minus 3 plus 3 times the ln of x squared plus x plus 1. All right, so that's a little bit better. Then what? Well, then we need to differentiate. And take care that when you differentiate, that y term is going to get a little extra attention or needs a little extra attention. So d by dx of all of this is going to be 1 over y dy by dx equals, why don't you take a moment and work on that right-hand side, see what you come up with. If you're watching this later, then pause the video and fast forward until you see me take that off. But see if you can't differentiate the right-hand side. Try and clean it up a little bit, maybe. So for the first one, it's gonna be 4 times 1 over my function, that's the easy part, times the derivative of the inside. What's the derivative of the inside? 2. Plus 3 times 1 over x squared plus x plus 1 times what, Nate?
Times 2x plus 1.
Times 2x plus 1. Perfect. So let's clean this up just a little bit. That's going to be 4 over 2x minus 3, and thanks, Nate, plus 6x plus 3 over x squared plus x plus 1. And all of this is equal to 1 over y times dy over dx.
Would it
Is
be
it
eight?
4 or 8?
8 instead of
8, my bad, thank you. Multiply both sides by y. So let's multiply everything by y. On the left-hand side, that y is going to cancel, and you get dy by dx equals 8 over 2x minus 3 plus 6x plus 3 over x squared plus x plus 1 times y. But y itself was equal to 2x minus 3 to the 4th times x squared plus x plus 1 to the 3rd, like that. Now, this form is going to look a little different than what we did earlier with the product rule, but this is the correct answer. WebAssign should accept this, no questions asked. If they don't, let me know. Now, Audrey, this one was yours. Let's compare it back to all the work we did with just the product rule and the chain rule a little bit before class. So we started out by calculating, this is f and this is g. We got f prime and g prime. And we put it in the product rule. And then to clean this up, I factored out the GCF here, which was your x squared plus x plus 1 to the 2nd power and 2x minus 3 to the 3rd power. You factored it out, that left some stuff behind. Distribute here, FOIL here, and then distribute the 3. Get a lot of cleaning up, etc. And then we end up with this. So somewhat similar. If you wanted to distribute the at least one of the 2x minus 3s and x squared plus x plus 1, you should be able to get the same thing here. When you distribute here, say one of these, then you get that to cancel out, distribute one of them here, you get that to cancel out, and you have some cleaning up to do, but they are going to be the same. Personally, looking back at this, I think I'm much happier to do it this way. I don't know. Audrey, what's your verdict? First way or the second way?
Definitely the second way.
Definitely the second way? All right, good. That's what I want to hear. So, nice. All right. What happened? All right, there we go. Still good. Let's keep going with example G. Any other questions or thoughts on example F here? Taylor?
It's just about like the log function. Since log is like an inverse function, when you do it on both sides of the equation, it's not like fundamentally changing it because both are inverse. So you can just factor that out. Maybe it's
Well, you're treating both sides of the equation the same, so the logarithmic function is a one-to-one function, so you can take the log on both sides and you'll be okay. Now, I guess kind of what we're assuming is that, we're taking the log of a positive quantity and, given the values of x, maybe that's true, maybe it's not, but it works out. It does work out. Okay, let's try example G. So this one's going to have some implicit differentiation and logarithm. Well, let's see. Let's just do it with implicit differentiation. So it's going to be y equals the ln of 5x squared plus 3y squared. Now that y squared needs to go kind of in brackets, or you're just gonna have to remind yourself, if you don't wanna put the brackets down, that's fine. You have to remind yourself that when you differentiate, you can't just do, oh, that's 6y. No, that's not gonna work. If you're differentiating with respect to x, that derivative is gonna be a little bit special. On the left-hand side, it's gonna be dy by dx. And I'll let you play around with the right-hand side for a minute, see what you come up with.
First, you could start 10x plus root of that, and you differentiate that part plus one. You can't distribute the log like that.
Okay.
No, there's no property like that. But you made that here rather than an example. Okay, we did the same thing. Guys are in the same way, like you can't distribute the log.
Alright, there's a lot of people here that want to distribute the log. You can't split this up as the log of this plus the log of this. It just doesn't work. There's no property like that for logarithms. So the property like it if this was a times, but not for a plus. So a lot of people are racing, that's okay. Better you make that mistake now than later.
Oh, 6 times, no, you put 6 times what the original thing is, right? Right? Cause all the other ones, like, oh no, we just did that Y on the other side, but I'm just.
I don't know where to put it.
Here, it's Y,
I tried to
right?
do like a plugin thing, This is gonna repeat the y hat.
Right, so then you'd have dy, I just know that it's one over. One over x squared plus 3y. Oh, how does still a y denominator? Oh, you have to replace that.
Natural logic is like this, instead of doing multiplication, it would be the natural log of both sides. Since that's not the natural.
Yeah, so the natural log of this whole thing, this itself is the inside function. So it's gonna be 10x plus 6y. But I don't know where to take it from.
Yeah, you gotta. You want me to get the derivative of y?
I don't know, yeah. So I don't know if I can do this.
This is a long. E to the power.
Okay, so for the benefit of my YouTubers later, one thing you can't do is you can't distribute the log. All right, this is, you just can't. You can't call this the log of this plus the log of this. It's the log of the whole thing. Now, when you differentiate your logarithmic term like this, let's go back to our handout. You get 1 over the function times the derivative of the function. That's just applying the chain rule. So once again, it's going to be 1 over whatever this is times its derivative. So it's going to be 1 over 5x squared plus 3y squared times the derivative of the inside. So I'm just going to write d by dx. I'm going to take the derivative of the inside, 5x squared plus 3y squared. I should probably write that with parentheses, etc. Let me continue over here. So it's dy by dx equals 1 over 5x squared plus 3y squared times the derivative of the first term. Derivative of this is easy, that's just going to be 10x. But it's that second part that we got to be careful about. And let me kind of squeeze in that bracket there, because we got to take the derivative of the outside times the derivative of the inside. Derivative of the outside is going to be 6 times y to the first power, right? I'm not going to write to the first power because that kind of looks like a prime, times the derivative of the inside. What's the derivative of the inside going to be? dy by dx. And that's kind of tough. It's like, oh wow, we got dy by dx in a couple places. But let's rewrite this and clean it up a little bit. All of this is in the numerator. So I've got 10x plus 6y dy by dx all over 5x squared plus 3y squared. Let me pause here for a second. Are we okay with this? A couple people wanted to put a 1 over y term here. How come there's no 1 over y term here? Yeah, we didn't start by taking the natural log on this. We just started with the derivative. Now there's a natural log over here, but there wasn't one here, so you just get your dy by dx term. So that's okay. Now, if you're stuck solving this for dy by dx, what I would do, what I always do when I have fractions, is I get rid of the fractions. I want to multiply both sides by the LCD of this expression. So that's going to be 5x squared, 3y squared, 5x squared plus 3y squared. And why am I doing that? What does it do for me that's worthwhile?
Cancel the denominator.
Cancel that denominator. So that leaves me with 5x squared plus 3y squared all times dy by dx equals 10x plus 6y dy by dx. Well, at least I got rid of the denominator. But I can't really easily solve for dy by dx because I got dy by dx on both sides. So here's what we're gonna do. And it's gonna be a two-parter. I'm not sure if there's a really convenient way to show this without skipping too many steps. I'm gonna distribute the 5x, or excuse me, distribute the dy by dx term here. 5x squared dy by dx plus 3y squared dy by dx equals 10y plus 6y dy by dx. 10y, thank you. Should be 10x. Since I want dy by dx by itself, let me move this term to the other side with the rest of the dy by dx's. So it's going to be 5x squared dy by dx plus 3y squared dy by dx minus 6y dy by dx equals 10x. Almost done. Since I've got all the dy by dx's on the left-hand side, I can factor out that dy by dx term. It's going to leave behind 5x squared plus 3y squared minus 6y dy by dx equals 10x. And finally, divide both sides by dy by dx. That'd be 10x over 5x squared plus 3y squared minus 6y. So this is an implicit derivative. If I wanted to find the slope of a tangent line at some particular point, not only would I have to give you the x value, but I'd also have to give you the y value in order for you to be able to do that. So this still does measure the slope of the tangent line, regardless of the fact that it's defined implicitly in terms of x and y, not just explicitly in terms of x. All right. Anything on this one? So the big trick here was really a couple things. One was when we were differentiating this, that we had to differentiate implicitly right there with respect to y. The other thing was our tricks in solving this. We got rid of the denominator, moved everything to the left-hand side, etc. Any last little thing here before we call this one a wrap? Yes, Rachel.
So we can leave the y in this one, we don't have
Yes.
to put it back from the beginning?
Yeah, we didn't have y solved for. If you look back at the beginning, let's look at it here. We don't exactly have an expression for y. I guess we could put this in if we wanted to, but it doesn't feel right somehow. But no, you're asked to differentiate implicitly. I kind of expect the y as part of your answer sometimes. So yes, nothing wrong with our y down here. Max?
When do you know when to plug y back into the final equation?
If you're using logarithmic differentiation, that's when you would plug in for y. Because with logarithmic differentiation, you can get a function that's just dependent on x. Kata?
Could you get the same answer if you take both sides to the power of e?
Where, right here?
Can't
That's a good
spell
question.
out
I would
log
think so. That's a good question. I don't know. I'd have to
halfway.
spend a little time calculating it, but I would think so. Not sure. Okay, let's call that one a wrap and then take a break.